to fight against a phase out of refrigerants. If anybody is, forgot the point of the AIM Act or hasn't been focused on it, just a reminder that the AIM Act comes from the EPA. Won't say anything about the EPA right now, but the goal is to address HFCs by phasing down the production and moving over time the consumption of refrigerants to refrigerants with a lower green global warming potential, right? So this is a phased approach, and you can see in the red box that the R410-A refrigerant is significantly more toxic and polluting than the other near-term refrigerants, some of which we'll talk about today, and natural refrigerants, which we will also hear a little bit about later on. What's really important here is that this past December, the New York State Department of Environmental Conservation, which takes cues, of course, from the EPA and the AIM Act, finalized their rule and their law on the phase out. And one of the things that happened was there was an elimination of the expected 1-year extension, which gave buildings until the end of 2025 to transition away from R410-A refrigerant. Again, the goals here are really important. It's a, highly polluting refrigerant when it leaks. The outcome of this law was, as of January 8th, any project with a permit, including the R410-A, has until January 1st of 2027 to be installed, meaning charged, started up, and so on. Buildings without a permit showing the R410-A would only have until January 1st of 2026. So this caught a number of people by surprise, not just design teams, but the manufacturers and so on. We all thought we had till the end of this year to phase away from this refrigerant. So there was a little bit of panic and confusion and so on for buildings that are, especially in HPD world, projects that are closing in the near term, where it's not really possible to make this transition right now if you are designed for a R410-A project, especially, I will add, with central VRF systems. And a couple reasons for that is there's a limited availability right now of equipment with the new A2L refrigerants. Also, there's some lack of clarity on the codes and rules for how to handle the new refrigerants, which are more flammable than previous refrigerants. So we were really concerned about this. Again, like I said, some folks raised the alarm, and we had to really start thinking about what are we going to do with all of these projects who don't really have an ability to transition right now. They have near-term closing deadlines, they have finalized designs, and so on. Here's where I cannot, here we go. Next slide, or sorry, on this slide, we just wanted to note a couple other considerations about refrigerants that came up as we're assessing all of this. One of them is that the larger VRF systems, and when we say large, I'm talking about 100 feet of line length, more than 5 apartments per system typically, require an annual refrigerant managed reporting to the state. That could add substantial cost to a project. And finally, and this is really key, and I think this should be a guiding bullet for teams that are thinking about refrigerants, is that the availability of R410-A in the future is expected to be limited. So that might really lead to some costs and challenges for buildings that need to recharge or repair their systems that have 410-A designed in. So we're going to talk through a couple of different solutions to get around this project and talk about sort of the applicability of different solutions. One of them is a variance process through the DEC. And then we'll talk a little bit about the transition to the A2Ls, some of the technical requirements, and we'll hear from, as I said before, Mitsubishi and LG about what's on their horizon. And then we're going to talk a little bit about a transition to natural refrigerants, in this case, a water-based system, which we think is a really compelling future transition away from refrigerants and the risk of leaks. I think a lot of folks on the call have probably been alerted through their HPD project managers or our TAP team about the concept of the impossibility variance. We've been doing a lot of outreach to make sure that projects that are, worried about this and are concerned would have a way to get around the requirements. The DEC allows for a number of different variances, but in speaking with DEC, we determined that impossibility variance is really the strategy that most of our buildings would need to work toward. And what that means is that an applicant or a design, a project cannot comply with these regulatory agreements. And the criteria, there's 3 criteria that are attached to this concept, right? One of which is a compliant substance is not currently or potentially available. I'm sort of summarizing these a little bit. And in this case, we know that some of the larger central VRF systems do not have new equipment ready for market right now. A variance will not increase the overall risk to human health. And that dovetails into another piece, which is that the applicant has used best efforts to address the impossibility and is making all efforts to really address the issue around leaks. As we understand it, a variance is not a guaranteed, but the DEC is working with us to figure this out. Again, hopefully most people have gotten this message, but we are going to work toward a blanket variance for eligible HPD projects. We know there's a lot of projects in this near-term period that are really not able to convert over to a new design or the new refrigerants. What we're talking about here are projects that are not just aiming, but really do plan to close before the 4th quarter of this year. We picked that point because we think that's when most new equipment will be available, and that's sort of an ample timeline. Again, with the impossibility element, it's where equipment, space, or information is not available to allow a project to transition. And we think this generally affects central VRF projects. And that's the messaging we've been sending out. And finally, to really reduce the risk of refrigerant leaks, we just want to reiterate that all projects have to follow HPD's technical guidance on refrigerant management. We'll share a link to where that document is. Anybody in the HPD world should already know about these requirements. They're referenced throughout HPD documents. Just a quick thing, if somebody has not seen the request for information for the blanket variance, we've sent out a tracker through our project management ecosystem, and we're asking any design team, development team to work with their HVAC consultant to fill this out. And it's got basic HPD project information, including the closing date and so on. And then there is more information that's necessary for the variance, which is actual information about the equipment in the project. And this is really important. We are going to collate this information and include it in our blanket variance. The due date was February 21st. We extended it to February 28th. We know that is tomorrow. We think a lot of teams are already working on this. If anybody's hearing about this for the first time, please let us know. We can probably give a short extension to make sure that we've got all of eligible projects included. So I am going to pass this over to Kevin McDonald from Stephen Winter Associates to talk about some of the technical considerations for switching to A2Ls.
All right, thank you, Jen. So I guess Jim was just talking about some of the options for, a variance, or if we cannot move to an A2L refrigerant, which are typically now R454B, or R32 are kind of the two main ones that are out there. But of course, if we can move to those where you are in your design process, that's the preference. There's the whole reason that we're doing this is that there's a lot less global warming impact to these. And we've done some, analysis that 3-4% leakage on a project can even start to make a electrification project from gas to electric potentially be, not as beneficial or break even as an environmental impact. So like the refrigerants have a very big impact on the kind of carbon output of a building over its life cycle. So if we can switch, we want to. Well, a lot of these considerations come from the fact that A2Ls are mildly flammable. So of course, there's more rules around these when you put them in a building. If we go to the next slide, please. But first off, I want to highlight that there are options on the market for these smaller split system heat pumps. So, 2 to 5 tons, mini splits and multi splits, one condenser per apartment, that sort of approach. There are quite a few options out there. What I have here on the right is just we pulled data from EPA's website, cold climate rated mini multi-split heat pumps in the 2 to 5 ton range. These were some of the kind of major brands that I have typically seen in the New York area. They're listed here, but you can see there's well over 300 kind of options of model numbers out there that have the R32 or R454B refrigerants. Now, this doesn't mean that they're necessarily ready to ship, but there's information out there. So you can check that website for other options, or we'll hear about some more from other manufacturers later. Generally, when you're going from an R410-A heat pump system to an A2L like R454B, which is probably the most typical, the performance, capacity and efficiency, they're pretty similar. So that's not the major, consideration when you're switching. It's the fire safety implications that we'll talk about later. I do want to note kind of initially, if you are very, very early in the design phase, going to something like a PTHP is certainly helpful, less refrigerant overall. There have been R32 PTHPs on the market. I think I did commissioning on one like 3 years ago. Like they're there and they have been. It's not as new. So we'll go over in a few slides, next few slides here. The A2L code requirements generally come from our current mechanical code, ASHRAE 15. I want to highlight that there are IMC 2022, 2024 A2L requirements, but that's not part of our jurisdiction. So we're focusing just in the ASHRAE 15 bucket. So if you go to the next slide, one of the kind of first more simple considerations is you have to protect the piping. This has always been best practice, even with R410-A refrigerants. If you put these pipes, these are the picture on the right here are water piping, but the same concept would apply if that was refrigerant piping. If someone can put a nail through it through the wall, obviously that's bad. We'd leak a lot of refrigerant. So there are some protections that are required. Generally, you're bracing and holding the refrigerant piping more than 1.5 inches, probably best to specify 2 inches for buffer, away from the drywall or sides of a shaft or any sort of location behind a wall, or you're adding 16 gauge steel to protect it. There's a link down below when these slides get sent around where you can read kind of the more specific code requirements here. If you go to the next slide, please, Jen. So this is a messy slide, and there's a lot of information in the detail on the right of a typical detail of what a ventilated shaft might look like. But this is one of the key components and one of the more challenging aspects to fit into multifamily buildings. Basically, because there's a refrigerant sinks, it can pool at the bottom, and it could be a fire risk. So we're ventilating the shafts, the fire rated shafts that these refrigerant piping travels in. And there's a few kind of design considerations here. So generally, you are venting from the bottom of that shaft, and you're that needs to discharge outside of the building, somewhere 15 feet above the ground or 20 feet away from window openings, and also not into open air ventilation shaft because it can pool at the bottom and be a fire risk there. At the top of these fire-rated shafts, there needs to be a makeup air opening, so you could draw air in from the top, and then the refrigerant, if it leaks, could fall out the bottom and then push out that exhaust pipe at the bottom. There's two different ways that you can approach ventilating these shafts. You can do natural ventilation or mechanical. So you can add a fan or you can do it naturally. If you're doing natural ventilation, that bottom vent needs to be pitched down. And basically this is kind of impossible in a multifamily building unless you're on the second floor or above, because you're not going to be more than 15 feet off the ground. So ostensibly we're looking at mechanical ventilation for most of the projects that you will be working on. If we are constantly flowing cold air through these shafts, then we know that they already do need to be air sealed and fireproofed, but there's just a thermal comfort consideration. There may be cold air in these pipes now. So just thinking about that as you're sizing equipment or adding additional insulation or going for this mechanical ventilation approach where you basically don't need to constantly ventilate except unless you have a refrigerant sensor in the bottom of the shaft that senses that there has been a leak. So the guidance on this is once again in ASHRAE 15, and there's a lot of nuances here, but you could think of 100 to 600 CFM is kind of typical for most shaft sizes. It's based on velocity. And then I would recommend a backdraft damper or something in those integral to the fan, so you don't have stack effect of from a thermal and sustainability perspective, having air constantly going through these shafts. The detail on the right, once again, is from Conquest Flame Power. They will do a kind of prefabbed ventilation shaft as an option, but certainly clear details need to be indicated for these for them to be successful on your job. Next slide. With all those challenges, obviously putting in those shafts and then finding a way to get the mechanical ventilation from the bottom of the shaft all the way up to the roof, that can be quite a challenge, and there's some planning and architectural planning that would need to happen there. So another option is to put the risers on the exterior of the building. I know there's an aesthetic challenge there, but you could probably make this a work of art, and it may still be more cost effective than handling a lot of the shaft requirements inside the building as well. So just consider, reconsider potentially exterior refrigerant risers. There's one more slide here, Jen. Again, there's flammability considerations. So just labeling the piping periodically that it's a risk of fire, flammable refrigerant. There are a few other considerations from FDNY that weren't necessarily explicit in the ASHRAE 15 code, but things I've heard are grounding the condenser and grounding the equipment so that there isn't a risk for ignition locally. And there may be some other kind of minor clarifications from FDNY or the DOB may be able to clarify in the Q&A session. These are not all of the requirements for A2Ls, but some of the major considerations that may affect planning overall for the project. I do want to acknowledge, and be on the slide before this or two before this on the shaft ventilation slide, Jen, if you can go back. There is a possibility that may be able to exempt from the shafts altogether based on using undercuts on doors within an apartment. And then you could look at the lower flammability limit or concentration limit based on the apartment as a whole, which might allow us to avoid this, but that needs to be explored with DOB. It does seem with a strict reading of the code that these shafts are required. So this would be the plan of attack unless other confirmations are made with DOB. And then I believe that may be the last slide that I have here. Yeah, thank you. We can discuss more, and feel free to put a question in the chat if there's a specific one, or we can discuss more in the Q&A section.
All right. Thank you for that, Kevin. I hope everyone can still hear me. So I think there's some questions about new equipment. When will it be available? As I said, we've got folks from Mitsubishi and LG going to do just super quick high-level presentations of where they are with the A2Ls. but will also be available in the Q&A to answer specific questions to the extent that the answers are available. So I'll pass this over to the Mitsubishi team. And guys, I'm really sorry your graphics did not come through exactly as you'd hoped.
Hi, Jennifer. This is Mitul Patel with Mitsubishi Electric, and we've got Sean and Alec as well. So just a quick introduction. I'm responsible for product management at Mitsubishi Electric for residential and commercial products. And then Sean will have a couple of slides and he'll introduce his role at Mitsubishi, as well as Alec after Sean. So just like you mentioned, Jennifer, this is just going to be a quick overview, but firstly, I just want to thank everyone for joining, and also thank HPD for hosting this meeting and for inviting us as Mitsubishi Electric to collaborate as we all navigate the significant industry change. So we at Mitsubishi Electric, of course, we remain completely committed to sustainability and electrification, and are fully invested in making this transition a success, especially for New York City's housing sector. We also recognize that by working together to balance the innovation with the practical implementation, we can ensure that the shift to low GWP refrigerants is both effective and beneficial for all involved. So as we develop products to transition to low GWP refrigerants, at Mitsubishi, what we did is we used the schedule provided by the AIM Act, which included that 1-year extended period for new installations, to completely redesign our about 500 SKUs. And our objective of the redesign was not only to meet the new low GWP requirements, not just the changing to a new refrigerant, but also to deliver even higher efficiency products with improved heating performance at low ambient temperatures, better, again, like I said, efficiency, and then also to make our products easier to install and service while maintaining the reliability, the flexibility that building owners and engineers typically expect, especially now when utilizing A2L refrigerants. So let's just run through the product launch schedule at a high level. As you can see, we've got dates there on the top. So January 2025, summer 2025, fall 2025, then January 2026, and then the actions that will take place listed below each one. And don't worry about the format there, Jennifer. Thank you so much. So firstly, the first transition, as was mentioned before, was for smaller capacity systems. That's less than 65,000 BTUs in capacity. And we've just begun releasing products and specifications and our selection tool, as well as started providing training to support this transition to match the AIM Act timeline requirements, while taking into account that 1-year extended period for new installations. So again, we use that additional 1-year extended period to make sure that we totally redesigned our products to be more efficient, and we use that additional time so that we could really get not just a facelift, but a total changeover in terms of our products, and making sure that we future ready as well. When it comes to our larger capacity VRF systems, so anything greater than 65,000 BTUs in capacity, we also recognize the importance of aligning our product development with performance data, application training, market readiness in terms of the needs of engineers, specifiers, contractors, and building owners, particularly in a complex and diverse building market like New York City. And thus we've structured our rollout a little bit differently compared to the single phase, less than 65,000 BTU product. So we're trying to provide more information ahead of time, given the longer required cycles of commercial building planning. So you can see from the timeline over the summer of this year, for larger capacity VRF systems, we'll provide product application training as well as submittals and specification data. And then into the fall of this year, we'll start doing installer training, as well as releasing an updated version of our product selection software tool, which will incorporate the VRF products with the clear design considerations and rules to properly specify the equipment to align with UL and ASHRAE 15 requirements, some of which Kevin previously went over. And then finally, in January of 2026, we'll begin shipment of the larger VRF systems to align with the AIM Act timeline requirements. And of course, we recognize that, based on what's going on here, that seems pretty late in the game, but that's the best that we can do, given that all of our product design and development was taking that extended period into consideration as well. So, of course, we recognize the industry as a whole is actively working to support the transition to low GWP systems, and we fully welcome any collaboration with HPD and all other stakeholders to ensure that engineers, specifiers, developers have all the right tools and information to confidently integrate low GWP solutions without unintended disruptions to ongoing and new projects, all while considering the realities of the product launch timelines. So a lot of words there, simple timeline. And then I think I'll thank you again, and I'll pass it on to Sean, who'll cover some design considerations as well.
Awesome. Thanks, Mitul. Hi, everyone. My name's Sean Daly. I'm a commercial area manager with Mitsubishi Electric, covering the New York City metro area. So I'm going to talk a little bit about some changes to ASHRAE 15 and design considerations that need to be made for the A2L VRF systems. So you guys are a little bit more aware of what's going to need to happen in these buildings to accommodate the A2L refrigerants. So just in general, ASHRAE 15 sets the max refrigerant charge for a given room volume. So, we're all used to working with R410-A, which uses an RCL, refrigeration concentration limit, refrigerant characteristic to set the limit. And that's a 26 pounds per 1,000 cubic feet limit there. Now, moving to R32, that's an A2L refrigerant. So they're not going to look at the RCL. It's at much lower than the R410A. They're looking at LFL, ASHRAE 15 for compliance. So that's a 19.1 pounds per 1,000 cubic feet. So we're a little bit less than R410A, not crazy less, but there is, we can't have quite as much refrigerant in a given space as we used to. So the new ASHRAE 15 2024 is the latest edition that has been published, gives us some new terms and calculations for the A2L refrigerants. So the calculations have gotten a little bit more complex than what we're used to with R410A, just looking at charge amount and room volume, some other factors to consider now. So one of the new terms is EDVC, that's effective dispersal volume charge. And essentially all that is how much refrigerant is allowed to leak into a given space or given room volume. Next term is MREL, or releasable refrigerant charge, and that's how much refrigerant will enter the space if a leak occurs. So in the past, with R410A, if a leak occurred, we had to assume the entire refrigerant charge was going to leak into that space. Now with the A2Ls and introduction of leak mitigation, that's not the case. So it helps us, to comply with this standard. So in general, how do we comply with ASHRAE 15 with A2L refrigerants? We have to make sure our releasable charge is less than or equal to our EDVC, which is the max charge that can leak into that space from a safety perspective. Next slide, please, Jennifer. So next, I'm just going to go over some design considerations for the A2L refrigerant systems. So, things are a little bit different, as Kevin went over with the A2L refrigerants. We have to be a little bit more careful on how we're handling these inside the building. So kind of the first challenge that we're dealing with right now is codes are not complete or final. So ASHRAE 15, they just released a new 2024 version within a matter of weeks with some additional changes. And, that seems to be a constantly evolving standard. There's still discussions around some addendums and revisions that may need to happen. And then the city and states are kind of following behind that. So they haven't really set their rules for A2L refrigerants and safety rules for how they need to be incorporated yet. Again, kind of waiting for ASHRAE 15 to make some final determinations. And the cities and states are always a little step behind what the higher level federal regulations are doing. So next, I touched on it on the previous slide. We're dealing with lower refrigeration concentration limits with the A2L refrigerants. So introduce those new terms, EDVC and MREL. Now they are allowing us to use leak mitigation controls. So I'm going to describe what those are in a second here. So it helps us basically reduce the amount of refrigerant that would leak into a space. And then finally, what are the lower refrigeration concentration limits going to result in moving forward? You're going to see smaller systems with lower refrigerant charges. Just, moving forward as we continue VRF designs, that's the way, the trend is going to turn towards smaller systems with lower charges. Just makes it easier to comply with the ASHRAE 15. So refrigerant piping, we got into it a little bit on Kevin's slide before with the fire-rated shafts and ventilated shafts. Again, there's some discussions about ASHRAE 15 kind of making that a little bit more lenient, but nothing's been finalized yet. So as of right now, we need fire-rated shafts when we have a substantial run of vertical piping within the building, and those shafts need to be ventilated. Kevin touched on this as a possible solution as well. Moving forward, you're probably going to see a lot more exterior refrigerant pipe routing, especially on those retrofit projects where you don't have space for the fire-rated shafts. Just something where you're going to see to comply with the code moving forward. BC controllers are still kind of a gray area as far as the code is concerned. We're waiting for kind of a determination as to whether they'll be considered part of the piping and not really a point of failure for leaks, or whether we need to have leak detectors and isolation valves on those BC controllers as well. So waiting for the governing bodies to kind of make a determination there. And lastly, with the A2L systems, I kind of mentioned it a couple of times here, we are going to be providing leak mitigation controls. So all of our FCUs on the commercial side will have a refrigerant leak detector built in. On the residential side, most of them will. And if they don't, I believe they will have the option for a field installed one. So that's all going to come from the factory. That's not something that engineers are going to have to worry about from a specification perspective. That will be provided by the manufacturer, at least for Mitsubishi's case. Safety shutoff valves also provided by us, the manufacturer. So they'll be at the BCs for our heat recovery systems, and for our heat pump systems, we'll have valve kits that can be installed loose in the piping. And lastly, all of this will be fully kind of plug and play, the leak mitigation controls from a factory perspective. We're providing all of the components and the control logic for the leak mitigation. So no additional control systems need to be specified or components. That's what we're looking at least from the Mitsubishi side of things with the A2L systems. And next slide, please, Jennifer. So that slide was just kind of general design considerations for A2L, designing A2L VRF systems. Here I kind of wanted to put the two major focus points if you had to convert a project over from R410-A to A2L, either R32 or 454B. So two of the main things we're going to need to focus on if we're converting a project is the refrigerant charge for ASHRAE 15 compliance. So you're going to have to calculate that EDVC for the zone served by the VRF. Again, that's your max charge that's allowed to be leaked into the space. And then based on that, you're going to have to increase room volume or reduce the releasable charge to get your releasable charge MREL under less than or equal to your EDVC. And you can do that kind of one of two ways. You can either increase the EDVC by increasing the room volume, connecting adjacent spaces, or using a ducted unit to serve multiple rooms. The other kind of method to help comply would be to reduce your releasable charge. The only way we can do that really is to get that isolation valve closer to the unit itself. And that would help reduce our MREL and hopefully get that under the EDVC. The other main focus point, other than refrigerant charge, that we're going to have to pay attention to is our pipe routing. So we touched on this before with the fire-rated ventilated shafts. So if refrigerant piping penetrates 2 or more floor ceiling assemblies, it must be in a fire-rated vented shaft enclosure. So 2 or more floor ceiling assemblies is not much, especially in the New York City multifamily market. So that's going to be a big hurdle for us. So if you can relocate the unit's piping to minimize floor penetrations and your shaft requirement. So whether that be running refrigerant piping external, kind of redesigning the layout of the systems so that your piping is serving a single floor or 2 floors and not going beyond that. we're going to kind of have to get creative on how we lay the systems out and route the piping to try and avoid some of these more restrictive requirements, like the fire-rated vented shafts. So that's all I have for the A2L kind of design considerations. And then I'm going to kick it over to Alec to kind of close out with the case for VRF, even though we're transitioning to A2Ls.
Hey, thanks, Sean. Good morning, everybody. This is Alec Del Vecchio. I'm a regional manager with Mitsubishi working out of New York City. As Sean mentioned, I'm just going to very briefly touch on the case for continued use and specification of VRF, even as we transition to A2L refrigerants. As everyone on the call knows, the goal continually in New York City is the electrification of heating and cooling systems. VRF really does remain the premier solution in that marketplace. And kind of utilizing some of the information Sean provided, I think we're going to be pretty easily able to retrofit some of our designs to accommodate the new legislation. So just very quickly, VRF is still the highest efficiency electrified HVAC solution. This is a cross manufacturer. This improves return on investment for building ownership and eventually will lower the cost for AC to the end user. Designed for occupant comfort, this really is an advantage for us as VRF manufacturers. We can provide a zone solution, allows us to decrease the overall size of the VRF systems so that we more closely align with these new A2L goals. That kind of ties into the next point we have here, which is increased installation flexibility. We can realistically design these systems in pretty interesting and funky ways to try and meet the goals here, whether it's, as Sean and Kevin had mentioned, routing piping external to the building or going with smaller systems or local systems. We can kind of very creatively retrofit designs, especially where there's not existing centralized HVAC infrastructure. This has always been an advantage for VRF and continues to be so. So yeah, we just really want to touch on the fact that VRF does remain the primary, in my opinion, solution for electrification. And while we do have to innovate here, we're going to be able to do so, and we will evolve to meet the new legislation for the city and the state. So thanks everybody for the time. That's it for the Mitsubishi portion here.
And thank you for that. Just some contact information that we'll make available, and I will pass this over to Brian to speak for LG.
Thank you, Jennifer, and thank you to my competitive colleagues at Mitsubishi. I was a little worried about how I was going to fit all that information into 5 minutes, and they did a great job for me. So thank you guys over at Mitsubishi. Just a little bit of a heads up. I'm just getting over the flu. If I start coughing or hacking, I apologize to everyone. But my name is Brian Bogdan. I'm the Senior Director of Engineering over at LG Electronics USA. I have been with LG just over 17 years. I've been in the industry about 25 years and have a lot of background in varying technologies, including chillers, variable refrigerant flow, many multi-splits, outside air products, and more. And I don't have the slide deck that you just saw, but I did want to add on to a couple of things here. The first thing that I guess I'll go to the next slide here. I don't know if I have control. There we go. So just a quick introduction of LG. We are a heat pump manufacturer. We have lots of heat pump products ranging from VRF to water heating and more. And our specialty is employing inverter technology that drives efficiency, capacity, and wide operating ranges, including heating at very cold outdoor temperatures. LG's inverter technology, our inverter heat pumps are quiet, and we design our compressors together with the inverter to help with operating range and drive greater efficiency, more heat at colder temperatures, and aid in moisture removal in the cooling mode. Next slide, please. I'm sorry. So as I understand, the big interest here is the greater than 65,000 BTU products. And I don't have a slide detailing it out, but did want to point out that that our timeline, really, for the same reasons that Metul shared with you from Mitsubishi, is very, very similar. We are shipping single phase products now. We continue to roll those product lines out. We are, by nature of single phase VRF, we're rolling out our indoor unit products for VRF. And then we expect mid-year to have materials and training to be coming out to prepare for the launch of the bulk of our three-phase product in the fourth quarter. So that's where we're maybe a little bit different than the Mitsubishi folks, but we're very well aligned by chance that with the rest of the industry on the way that we're rolling out products. And I wanted to I guess recap what you heard from the previous manufacturer, that R32 offers higher capacity with smaller charge. It gives us an opportunity for higher efficiency and packing more capacity to smaller footprint. What you're going to see from LG is we're going to deliver more capacity in a smaller number of frames, which helps with the overall refrigerant charge of the system. Features and accessories, we're incorporating a lot of helpful features into the design. We're going to have sensors built into the indoor units as standard from our factory. We are going to offer shutoff valves to minimize the releasable charge. Those shutoff valves will come in two flavors. One would be just shutoff valve boxes that may come in single or 2, 3, 4 port options that would look very similar to the heat recovery systems that we sell today, but would be applying ways of applying shutoff valves to heat pump systems. We're also going to integrate shutoff valves in our heat recovery units, and to make that easier, so there's no additional installation requirements. And then design and layout tools. We believe this is kind of an important topic, that a lot of the challenges that the Mitsubishi gentleman shared with calculations and all, and I do want to point out that some clarification. I know that it was shared that we're looking at LFL and 19.1 pounds per 1,000 cubic feet as kind of the baseline, but I do want to make sure that we're understanding that it's not exactly that you can just, if you're under 19.1 pounds per 1,000 cubic feet, you're good. There's plenty of calculations in the ASHRAE 15 standard that help you with determining how much of the room volume you can take credit for, what counts as a connected space, and various other things. And so that I'm going to call it refrigerant concentration limit, but the concentration limit you end up with is significantly less than LFL. In certain situations, the baseline is more like 25% of LFL, and you may be closer to 50% of LFL with certain requirements resolved. And I'd also like to point out that UL has very specific requirements for designing products in ways that can be applied safely within the standard. Within UL, there's an enhanced I'm sorry, ETRS. I just drew a blank. Enhanced tightness refrigerating systems. Enhanced tightness refrigerating systems allow us to do additional things and give more confidence that the products are a lot less likely to leak and be tighter refrigerant systems. They also appear to open up some opportunities for other mitigation factors such as circulation and some other things. And so our equipment on the nameplate will be stamped with an ETRS designation, which indicates that we meet the enhanced tightness requirements in UL. Also want to point out, with heat recovery units, this was a discussion that I had with our R&D teams quite some time ago. But in UL, there is requirements for what you have to design into that heat recovery unit, or anything that's not an indoor unit in the building. In our case, that's predominantly heat recovery units. But the internal design dictates whether or not you need ventilation connection to that unit, refrigerant detecting inside that unit. And I'd like to point out that the LG design will be accommodating those requirements and avoiding the need for a ventilation connection. So that's something I wanted to share, but with all of these challenges in the calculations, LG is going to provide some calculator tools, software-based, one of them being RChecker, which is really a more residential-oriented software that helps with calculating room volumes and dispersal volumes for refrigerants for systems. And we're also going to integrate these calculator tools into our LAT software, which you may be familiar with for laying out VRF systems. So that's really what I wanted to share today. I think there's a lot packed into one slide here, but moving forward, my contact information was on the first slide. And I do want to make sure that I share our rep contact information, John Moore from Clima, New York. His contact information is here. And John and the Clima team are first line of defense to help support you through this transition. Thank you.
Thank you for that. Appreciate that. Now, as I expected, as I mentioned, we're going to have a really interesting conversation about something that is a little bit different with the system using water to transmit heat around the building. So let me introduce Nicole Cece from Stephen Winter Associates. And reminder, we've got time at the end for a chat. And if people are continuing to put questions into the Q&A, we will try to answer what we can after the presentation or in the Q&A function.
Jen, can I make one note? While you had that slide up there with the natural refrigerants, I think it is worth mentioning that this is one step, and then eventually we move towards whether it's natural refrigerants or ultra low GWP refrigerants in the near future. So we're not there yet, and it's not even worth talking about what those products are because there aren't really enough for the market. But this is kind of a step down, and then there'll be another further on in the future.
Thank you for that, and I'll pass it on.
Great, thank you. So I'm Nicole Cece with Stephen Winter Associates. I'm a principal mechanical engineer out of our New York office, and I'm going to give a brief introduction to hydronic electrification, and that can take a lot of different forms. So I'm going to kind of juggle between some information about the system as a general concept, what some variations on it might look like, a few key points distinguishing it between alternative options like VRF or PTHPs, and I'll throw in the tiniest bit of cost information at the end, but just being upfront, we don't have a lot of data. All right, next slide, please. So the basic approach that I'm talking about is one where we have a normal hydronic distribution running through the building. And that distribution is connected to what I'd call mild temperature terminal units. And I'll get into details on some of those terminal units in a couple more slides. But we're talking about distribution and terminal units that operate with a loop temperature of roughly 100 degrees Fahrenheit in the winter, 85 in the summer. And there are a couple of important points to call out about those temperatures. So one is that when we get below 105, we obviate some of those energy code requirements, the code requirements for piping insulation. We also, when we get below roughly 110, it's a squishy number. When we get below roughly 110, we become compatible with a really wide range of air-to-water heat pumps that can feed that loop. And also, by not using chilled water for cooling, we're also eliminating the potential for condensation to get on pipes, preventing corrosion, premature failure of that distribution piping. So that's our distribution within the building, terminal units, and then we're feeding that loop with air-to-water heat pumps to inject heat into the hydronic loop and adiabatic coolers to reject heat from the loop. So air-to-water heat pumps to inject heat, adiabatic coolers to reject heat to maintain our target loop temperatures. A lot of air-to-water heat pumps can also reject heat. It's just the adiabatic coolers tend to do that much more efficiently. And then we also have a lot of other options for replacements or supplements to those central plant components. So for example, wastewater heat recovery and ground source fields, those are probably two of the more mature options. And then lastly, domestic hot water. In the architecture as we tend to use it, we're typically getting domestic hot water from a water-to-water heat pump that is connected to that same building hydronic loop, if we're not picking up that DHW load from wastewater heat recovery or ground source. And producing domestic hot water off the loop, that lets us recover heat in the cooling season. And then in heating season, it does add load to the central plant. You can use other systems for DHW as well and just decouple it from the hydronics. You can have a standalone DHW plant. I just want to call out that if you do go with that approach, then you have to deal with routing dedicated piping and services from outdoors to the mechanical room, as opposed to this option, which is just stick a water-to-water heat pump in the mechanical room connected to the hydronic loop. Okay, next, please. So we run into a lot of hurdles when trying to electrify our buildings. And we don't magically solve every one of those problems by going with an electrified hydronic system. But I will argue that the items that are listed here in the orange box, we can deal with them a little bit more easily when we go with an electrified hydronic system as compared to VRF or some of the other solutions that are on the table. So those obstacles that we think we can overcome or at least make a little bit less difficult by going with the hydronic solution. First one, we do avoid charging residents for heating and domestic hot water because the terminal units use very little power for heating. And VRF is similar in that regard. The difference is that with this solution, we have a lot of options for keeping most of the cooling cost on the residence meter in the hydronic approach. And then domestic hot water stays on the house meter. We don't have excessive wall penetrations, which can be a concern with PTHPs. And then space availability. So when we're using hydronic distribution at low temperature, we're using water piping, and it doesn't need to be boxed out like A2L refrigerant piping does. And if we keep it below that 105°F temperature, it doesn't even need to be insulated. So that leaves us with a really small chase footprint that's required. When we get down to new systems, we know new systems, they trigger new maintenance requirements, new staff training. And hydronic distribution is well known. We have a lot of hydronic systems in New York. And the other components of the system are all packaged units. And I would argue that it's a little bit easier to train or develop maintenance contracts and practices for a piece of packaged equipment as opposed to a full system with cascading components. But I want to be clear, I'm not saying we've solved this concern. We definitely haven't. I just think that the hydronic approach gives you a little bit of a small win in this front. Then refrigerant issues. We know leaks are an issue, and we know leaks in split system piping can be a big problem. Leaks in packaged equipment are also a big problem, for sure, particularly at end of useful life when refrigerant needs to be recovered from that equipment. I think it's a little bit more feasible to avoid and reduce leaks in packaged equipment than in piping systems. I don't think we have a lot of great data on this, so that's why I'm putting some asterisks up here. And then regulatory phase outs. Those are definitely easier to deal with when you've got systems where your refrigerant is in packaged equipment. At end of useful life, you're going to be replacing that packaged equipment. You can swap it in with new generations of air-to-water heat pumps or terminal units, water-to-water heat pumps, etc., all while maintaining your same distribution system. So those are the items in the orange box, the ones where I think an electrified hydronic approach gives you some wins. The other items on this list, we're not fixing. Cost is high. Cost is high for this system. It's high for a lot of electrified systems. And like other electrification options, like most electrification options, energy costs are very difficult to lower when we're comparing against a gas baseline. Okay, next slide. So continuing from that previous slide, I want to touch on a few more benefits for that we see with the electrified hydronic system. Up top here, I've got some EUI information. This comes from some energy modeling we did. And again, there's an asterisk on here next to VRF because I feel that VRF systems tend to be modeled with kind of an overly rosy efficiency. I think some of the data that we've seen from the real world shows that some of the COP numbers that we've been using in modeling are probably a little bit higher than they should be. So that's why there's a little bit of an asterisk on that line, a little bit of wiggle room to the EUI numbers associated with VRF. But I want to call out that the electrified hydronics approach in our modeling looks pretty comparable to the energy performance of the VRF system. And I wanted to use this slide as an excuse to take a minute to talk about some of the non-energy benefits. So I think the idea of water as an open source medium is really important. It isn't subject to phase outs. It follows basic laws of nature. You can pipe in equipment from any manufacturer you want. You can change your selections every time you want to replace a unit. You can mix and match components that are connected to that piping network. You can expand loads. You can decrease loads on the loop. You have a lot more flexibility than you have with a factory designed refrigerant distribution that's like factory locked in, like you have with split heat pump systems. And then these last couple points here, I touched on the use of sealed refrigerant circuits previously. I think that carries some benefits. And lastly, this system does allow for simultaneous heating and cooling and space cooling in all units at all times. And access to cooling is important from a safety, health, and equity perspective. Okay. So I mentioned that I would dive in a bit more about terminal units and where that simultaneous heating and cooling ability comes from. There are a lot of different terminal units that could be used with this system. It's an open source system. I tend to like the hybrid water-cooled ACs because they use a low temperature fan coil for heating, and then they also use a water source heat pump section for cooling. So that gives you the simultaneous year-round heating and cooling ability. And it does it on a two-pipe system with, when we have that hydronic loop operating in the temperature ranges that I established kind of in the earlier slides. So this approach, it keeps our heating cost on the house, very little power for the terminal units. And because we are using that water source heat pump section to run cooling, most of the cooling cost remains on the terminal unit. These are also console units. They have onboard controls, so no integration required there. But that said, there are a lot of other terminal unit options that can work with this system. We've seen this done with fan coils on a seasonal switchover. We've seen it done with no cooling. We've seen this with water source heat pumps. You could probably do a radiant option as well. You could really evaluate, I think, just about any terminal unit that would work with that low heating hot water temperature. Okay. So I wanted to call out that this system also works in new construction applications. It also works in retrofit applications. The terminal units that we propose, they tend to have the same flow rate as a typical baseboard or other hydronic terminal unit, meaning that existing hydronic distribution networks are often right size for use in this application as well. And you can also even reuse steam piping in many cases to convert it to hydronic application for this use. So if that steam piping is sized okay, it's usually reusable for hydronics. We've seen plenty of cases where it's fine to use. That said, we've also seen some where the return line is a bit too small, or it's a one pipe system and additional lines are needed. So it's a case by case item, but I think it's doable in a lot more cases than most folks realize. And if you can reuse any existing piping, that's a big win for minimizing disruption. Alternate options involve either cutting sleeves in everywhere or running new refrigerant risers and boxing out chases potentially. We're trying to minimize disruption and how invasive things are for residents. We also often can reuse an existing air conditioning circuit for some of the terminal unit options that are available on the market today. And that can help us avoid expensive and invasive rewiring in apartments. And last bullet point here, I want to note that there is a displacement strategy modification available. There's an option on the table with this system, because again, it's flexible, it's water. So in that displacement option, you would size your air to water heat pump plant to be equivalent to roughly the size of the existing electrical service capacity that you have to work with in the retrofit. And that way you'd avoid doing an expensive electrical service upgrade. And then you would use fuel-fired boilers to meet the rest of the peaking load. And just to give folks a rough idea of how this works, the rough ballpark on it is that you can often meet over 80% of your heating load by using this strategy. And when I say heating load, I mean you can meet 80% of your annual heating energy usage with this strategy. So it can be a great way to dramatically bring down costs and interruption while still offsetting a huge amount of buildings' baseload fuel usage. Okay, next slide, please. Yeah, so running through what this looks like in a typical retrofit. We're starting off on the left with a hydronic baseboard building, window air conditioners or sleeve air conditioners. We've got a gas-fired boiler plant in the basement. It's feeding an indirect water heater for domestic hot water. And then we go through a few steps to convert it. So we're reusing those existing hydronic risers. We're replacing our terminal units with the low temperature units, the low temperature heating units. In this case, the hybrid water-cooled AC. We're installing a water-to-water heat pump in the basement to make domestic hot water off the loop. We are lowering that hydronic distribution supply temperature, and we're installing air-to-water heat pumps and adiabatic coolers up on the roof here to maintain the loop temperature. And then we can also layer in additional heat source and sinks like the wastewater heat recovery and ground source. Okay, and the final slide here. Thank you. So I mentioned I would share some numbers. I don't have a ton of good numbers. I don't have any good numbers for what this costs in new construction. I have a few data points for retrofits just because it's very early days with this kind of system. What I can share is just being very upfront that incentives are always a moving target. They've been especially tricky with this kind of system. A lot has been moving. Projects that we've worked on or some projects from other firms that we've reviewed have taken advantage of some combination of Con Ed clean heat, NYCRR low carbon pathways, investment tax credit, 179D. Those are very much up in the air now for a variety of reasons, and NYCRR heat recovery. So because those incentives have been moving so much lately, I'm focusing here more on the pre-incentive costs. And I'm showing just a recent project's design phase contractor pricing, which came out to approximately $45 to $60 per square foot. We've costed this system out a number of times and seen it coming in within roughly 5% of the cost of a VRF retrofit. And those are both expensive. That said, I see a lot of variability in this pricing. I mean, $45 to $60 per square foot is a lot of variability for one building. And a lot of that variability we're seeing being driven by which air-to-water heat pump options we go with. In this particular example, the lower end estimate is a project where we pivoted to using the LG Hydro Kit actually as the basis of design for heating the entire building loop. I think it's also important to note, I've talked with a number of manufacturers reps and found that the piece of equipment cost for an air-to-water heat pump can be roughly 10 to 20 times what a gas boiler costs. So first cost of just equipment is extremely different for an air-to-water heat pump versus a gas baseline. And I also want to note that when we look at a displacement strategy, the costs get a lot better. Once you're meeting most of your heating load with air-to-water heat pumps, your installation cost per MMBTU of heating load met, it really jumps up. It's not a linear increase. So I said at the beginning of this presentation that we hadn't solved the high cost issue for electrification, and we haven't, but I'm hoping that I've shared enough other information about this system to show that I think the architecture really has a lot of wins to it, and hopefully it helps solve some specific project constraints, especially when we're looking at this compared to some of the alternate options on the table today. And thank you. That was my last slide. I'm happy to answer questions, and I'll also throw my email in the chat for any follow-ups. And I have a big study that we did for NYCRR modeling this kind of system that I can circulate if anyone really wants to do some not so light reading on this.
Thank you so much, Nicole. And I will say, all of our presenters went a little bit long, but these were super informative, amazing presentations. So I think a lot of the questions people had were answered in the presentation. There are answers coming through on the Q&A. I just want to leave folks with two quick things. Reminder, in terms of solutions, if you've got your permit with R410-A already, you don't have to do anything except get your system installed, charged, and started up by the due date. If you have a permit, you're closing in the near term, and it's really, truly impossible to convert to A2Ls. Seek a variance. You can be part of the HPD blanket variance. Please let us know if you are in that situation and you did not receive the matrix. If you have a permit, if you don't have a permit and you can reasonably transition over, that is the best strategy. This will make your project more future-proof around particularly getting R410-A in the future. Again, a lot of systems already have this available if they're smaller, packaged, and so on. And finally, if you are past the threshold and you are closing toward the end of this year or beyond, now is the time to start thinking about what you learned today to redesign to a system with A2Ls or something else, or a hydronic distribution system like Nicole talked about. Think about refrigerant leaks, please, and the future availability of R410-A when you're making your decisions. And finally, this variance project we're working on, please, if you have the spreadsheet, get it done, send it to us by tomorrow, sustainability@hpd.nyc.gov. Please put the refrigerant in the subject line. We have pretty specific instructions so we don't lose your emails. And if you have questions or didn't receive something and need it, you can reach out there. I am going to stop sharing and try and take some questions from the Q&A. And sorry, I've not been able to really effectively monitor this while I am advancing slides. So if anybody, maybe Kevin, you've been looking at them, or DOB folks, you want to jump in and answer any of the questions you saw?
Thanks. Yeah, there are a lot of questions there. I don't know how to even hit on a few of them. Certainly, just to summarize in general the themes, there's plenty about clarifying the A2L requirements and approaches to satisfy those requirements. I think those are great to share, and please continue to share because it's evolving. We're all looking for what is the cleanest path forward on these. So thank you for the questions. Please continue to submit more. We'll review and share follow-up after the meeting. But I saw a hand up as well. Are we taking verbal questions?
Sure. We can take a hands up question because the other ones we have in writing and can address. I can't see a hand though, so I can't answer that one. Oh, I see Brian has a question. If you want to jump off mute, I think you should be able to ask it.
Really quickly, Jen, before Brian, Dana had her hand up first, and I believe your mic should be able to unmute. So please feel free to hop on and ask your question.
Great.
This is true.
Thank you, Jasmine. This is Dana Fisher with Mitsubishi Electric. I really appreciate all the different manufacturers that jumped on there. There's no doubt that there's so many different technologies. I think the real issue with the transition that was announced is really the discrepancy between the latitude that's provided with the AIM Act versus New York City, and the fate of VRF projects and installations and designers over the course of this calendar year. Whether they're going to get projects completed this year, or where everyone else in the rest of the country would have latitude into next year. And so I know that you're in the process of the blanket variance, and that's very encouraging. Any additional detail that could be shared about what is the criteria that the DEC has conveyed about seeking those variances and their latitude in providing that for VRF would be very instructive to, I'm sure, many of the designers on the phone, just because of the uncertainty in the building process over the course of this year and the tremendous risk that's placed on those developers.
Suzanne, if you are still on, would you be able to field that question? Let's see if Suzanne from DEC might be able to answer. I don't. Oh, here you go.
You may have to unmute her.
I have no idea how to do that.
Okay, I'm looking for her. 1 second.
Oh, here, I got it. Sorry. Least technical savvy person around.
Thank you. We also use Teams and are familiar with how hard these events are to run. And this has been great, actually really informative. Thank you for inviting me. I also put in the chat our email address and the link to the main website for the rule that has a fact sheet, an FAQ and whatnot that actually covers some of this, the questions. I could not see the QA. All I get is some weird Microsoft icon saying I can't access it. So sorry if I didn't answer your questions. And to the question about, you know, we have an exemption that allows you more time, like you mentioned, Jennifer. There's also the variance process. There's other mechanisms that agencies have. I would direct those questions to us rather than HPD. So feel free to reach out, you know, to DEC directly on those questions.
And I will add to that DEC's been doing a really good job of keeping an up-to-date FAQ published so that all the questions that get answered are available to folks. Thank you for that. Brian had his hand up a couple times. I'm gonna pass that over to Brian McDonough.
Great, thank you. I will keep it brief. 2 questions really. Well, question number 1. So in ASHRAE 15, there's a reference to another ASHRAE section known as ASHRAE 15.2. They call it, it's known in plain language as the low-rise residential refrigerant code. And the requirements on that are a little bit less strict than ASHRAE 15. So I was just curious if anybody had any feedback and thoughts on that. And my second one is just to confirm, so the extension on the 3-phase equipment has been removed. If you don't have a permit, single phase or 3-phase just needs to be installed by January 1, 2026, is my understanding. And to recap, number 1, ASHRAE 15.2, is there any feedback on the applicability of that? Because that appears to allow for a bit more flexibility in how you lay out your system. That strictly appears to be required for one-to-one systems. And question number 2 was basically January 1, 2026, if you don't have a permit, single phase or 3-phase. Thank you.
Sorry, I don't know if Sean has his hand up to answer the single unit or single apartment. I don't know if anyone has an answer to that right off the bat. So we'll have to take that home unless somebody take that home and get back to you. Unless somebody jumps in and answers it. As for the single phase question that you asked, I again will defer to DEC on that.
Yeah, I'm not sure how to answer that. Sorry, that question. But I'm happy. I again put our email address in the chat, and we have been responding to about 10 to 20 emails a day lately. So please feel free to reach out. And plus, really, it's been very helpful talking to New York City. It's very helpful hearing from all of you. We hear from manufacturers a lot. We don't hear from a lot of other entities. And the more questions you get, the better we're going to get at adding, you know, making these FAQs, doing enforcement discretions, doing variances. Like we need to actually hear from people, which we would have heard from more people during our proposal phase. But please don't hesitate to email us. And if you don't get a response, keep emailing us because we do want to hear from you and we want to get the information out.
If we do take those motors down from the cooling towers and we want to store them in the cellar during construction.
Sorry, I'm not sure if that was a question or somebody speaking just that got slipped through the microphone. So I'll assume that was just a slip. One other thing I'll say, and then sorry, I can only see some hands at a time, is that the building department and DC are working really closely together to figure out, how this shows up in the requirements. So stay tuned for that. There were some questions in the Q&A earlier about the permit definition and FDNY requirements. So guidance is forthcoming and they're working together on that. Sean, you had your hand up.
Yes, thanks, Jennifer. Brian, just a great question on the ASHRAE 15 versus 15.2. I was discussing that with a colleague earlier today. We're a little confused by the applicability of it as well. If there is a cutoff on the multifamily side of number of dwellings that pushes you from 15.2 to 15. So that's a question mark that we have as a manufacturer as well. And the way I understood it, your second part of your question is correct. You have by the end of the year, if you don't have a permit right now for either single phase or three phase. So great points there. I just want to mention, I put it in the chat. We do have a full lunch and learn presentation on ASHRAE 15 A2L design. If anyone's interested, please reach out to me or someone else on the Mitsubishi Electric team. And we also do currently have hybrid VRF systems available in the US, which is refrigerant between the condensing unit and the BC branch circuit controller, and then water from the branch circuit controller out to the fan coil units, the terminal units themselves. So hybrid approach there, a little different from the hybrid approach that was talked about at the last hydronic section. But if you guys anyone's interested in learning more about that, please reach out to someone at Mitsubishi.
Thank you for that. So it's 1 minute before 12. I don't see any other questions. We have record of all the questions in the chat. We'll try and make sure that we can answer them. If anybody has questions, again, Mitsubishi and LG can answer product and more broad questions, and DEC as well for regulatory questions and so on. With that, I thank everybody, especially our technical team and all of our speakers and the manufacturers. That was super enlightening for me. It's a really complex transition. We all know that. And thanks for everybody who joined this webinar.
Thank you.